we will start talking about work. Now, work, as you look at it, is different than what we're probably used to. Work, we just think we're getting paid to do something. Work in a process of physics is different by definition. Work is the product of the magnitude of displacement times the component of the force parallel to the displacement. That's a mouthful. The key to work is we have to apply a force, and it has to move, the object has to move in the same direction that we are applying the force. So you got to have movement of the object, so you got to have displacement, and you also have to apply a force. So the unit for work is joules. Joules is derived from taking 1 Newton, which is force, times 1 meter, which is displacement. Now for work in general, we use this equation. Work is equal to force times distance times the cosine of theta. We'll talk about what that means here in a second. But we want to make sure we include this in our definition, cosine of theta, in our equation. So here's an example. This person has a box, and they're pulling this box with a rope, but the rope's at an angle, so it's not parallel to each other. Which means by pulling on the rope, there's 2 types of forces. There's a force that's going to be the X and a force in the Y on the rope. Because work only applies to things that are parallel, we only do or deal with the X component of our force. So we have to find what that is. And by trig, we use this identity. Force times the cosine of theta gives us the parallel force. So that's why we include that cosine of theta on there. So if we're at an angle, we can just pop it right in the equation and go. We don't have to draw a triangle every time. Now, in this situation, this gentleman is carrying a bag and walking this way. Now, the force that he's applying is the normal force upward. So the force is going up, but the displacement's going here. When we're perpendicular, even though it's a heavy object, okay, and as we lift it up, we're doing work. If we leave it level, well, applying a force upward, but moving this way, because we're perpendicular, no work is done. So again, the forces have to be going in the same direction as the displacement. They can't be, or have to be parallel to the displacement. They cannot be perpendicular. If they are, no work is done. So what seems like could be work, for us, by definition of physics, is not. So here's some math, and here's some and things that we can do with math. So here's an example. An intern's pushing a patient of 72 kilograms on a 16 kilogram gurney, producing an acceleration of 0.6 meters per second squared. How much work does the intern do by pushing the patient and gurney a distance of 2.5 meters? Assume there's no friction. We'll get to friction later. So when I look at this, first thing I want to do is I want to go work is force times distance cosine theta. Okay, I know that's what work is. What do I know? Well, I know distance, and I know my angle. It's a flat angle, so it'll be 180 degrees, right? So I know cosine of 180 degrees, or you should, if you've taken geometry, is 1. So this is going to be 1. So work is going to be equal to force times distance. But I don't know force. I know distance, but I can figure out force. Remember Newton's second law, F equals ma. So the force that our intern is applying is equal to the mass of this object, which is the mass of the patient, plus the mass of the gurney. So 72 plus 15, 87 kilograms, times the acceleration, which I know is 0.6. So if I take 87 times 0.6, I get 52.2 newtons. That is now my force that I can put in here. So to find the work done, I take my force of 52.2 newtons, and I multiply it by the distance of 2.5 meters. And the work being done, in this case, is 131 joules. So we can use Newton's second law to find force that we can use then to find work. Another example, here we're going to use the whole theta thing. Again, we know work is force times distance cosine theta. So in a gravity escape system, this lifeboat in a large ship is deployed by letting it slide down a ramp and then continue in free fall to the water below. Suppose and this is the mass of the boat, slides a distance, which we have here, at an angle of 60 degrees. So right away we know we have an angle. How much work does gravity do on the boat? So what I want to look at then is try to figure out what I know. I know the angle, I know the distance. Again, I don't know force, but we're talking about gravity, and the force of gravity is mass times g. So the mass is 4,900 newtons, and g on Earth is 9.8. I take 4,900 by 9.8, and I get, and I'm just going to round this to these two sig figs, 48,000 newtons. I think there's a little bit left over, but we'll leave it there. So now if I want to find work, I take my force of 48,000 times my distance of 5 times the cosine of my angle, which is 60. And I just make it one giant calculation, and when I solve for this, I get 120,000 joules. So that's using the angle. Here's a situation. So we have 4 boxes, and these boxes are moving a horizontal distance the same as d. The force applied is the same magnitude, so we'll say 5 newtons. However, the direction is different. So let's think about this and which one has the most work done, and what we want to go from increasing work done from negative to positive. So we want to go least work to most work. Well, right away, for work to be done, they have to be parallel. So we know in this case that this is for sure our greatest. Okay? That's going to be our highest. That's going to be number 4 because the lines are parallel. Now let's look at the other lines. Is anyone that can have a line that's parallel? Well, on C, we have an x and y component. So a portion of this force is going to be parallel. Therefore, case C will be my 3rd highest. Okay? And now I want to look at A and B, and see which one is going to have work done. Now, in the case of A, they're perpendicular to each other, force and displacement, which means my work's going to be 0. So I have no work in case A. But in case B, and here's what's important, my displacement is going this direction, but my force is going in the opposite direction. So if I take force times displacement, since my force is going the opposite direction, it's going to be a negative number. Work done in this case is going to be a negative answer. So 0, negative, which one's greater? Well, obviously 0. So that's going to be my 2nd greatest, with B being my least. So if I'm listing these from least to greatest, I'm going to go B, A, C, then D. And obviously you heard my reasoning behind it. Okay, lastly, we're going to play this game called Rock Hero, obviously made up game. We're pushing the drum set to slide it into position. We're exerting a horizontal force of 24 newtons. Okay? Kinetic friction opposes the motion with a force of 22 newtons. We slide the drums a distance of 1.5 meters. The weight of the drum set is 54 newtons. What is the total work done on the drums? So you can see my free body diagram is here. And the first thing I want to look at is in the vertical here, the y component. Since we're on a flat surface, normal force and gravity are equal. So there's no work done in the y. So work in the y is 0. So obviously when we're talking about this thing moving, it's going to be in the x only. But we have 2 opposing forces. We have our applied force and friction. So we can take the work and find the total work done. We can just add it together. So we can take the work from the applied force and add it to the work from friction, and that will tell us our total work. So let's talk about the applied force first. Work applied is force times distance. So for the work applied, our force is 24, and our distance is 1.5. Okay? And so we'll take 24 times 1.5. Then we'll add to that friction. Now, friction, our work for friction, is going to be a little different. Our force is 22, but it's going in the opposite direction. So it'll be negative 22. Again, friction's a negative force. But we're also going to be pushed over the same distance, so 1.5. So negative 22 times 1.5. So we got 24 times 1.5 plus negative 22 times 1.5. And when we do all this, and you can do the math on your calculator, you will get the answer of 3 joules of work being done to do this. So I'm only doing 3 joules of work. Hopefully this makes some sense to you. Again, if you have questions, I'm always around.